Welcome back, AP Statistics. This is Chapter 17. We're going to be talking about sampling distribution models. This is the point in the year where we take a pretty hard left turn. We've been talking about probability recently. We are now going to kick it up a notch. This is one of the more obscure topics in AP Statistics, but if you can get this down, this will unlock what we will be doing pretty much for the rest of the year. So there is a bit of a learning curve to this, but you're used to that at this point. You guys are rock stars. You'll get it. Sampling distribution models. Here we go. So, what is a sampling distribution? Featuring our friend Garfield. So, we're going to let X, our random variable, be the weight of a cat. And as I observe, Garfield might skew our data. If you know a little bit about Garfield, he likes lasagna. Anyway, say we took a sample of 30 randomly selected cats, maybe Garfield in there too, and found their mean weight. We could call that X bar sub 1. All right, why the subscript of 1? Well, we're going to be doing this a lot. Suppose we did it again. We sampled 30 more cats and found their mean weight. We could call that X bar sub 2. Let's say we kept doing this over and over and over and over again, and we would find X bar sub 3, X bar sub 4, X bar sub 5, each sample mean coming from a sample of 30 cats. Doing this, we would be learning about the distribution of the sample mean weight of a cat. Some of the means are going to be a little higher than others. Some of the means are going to be a little low. So we get an idea about how the sample mean is distributed, in particular for samples of size 30. Since we're learning about the distribution of a sample statistic, in this case the sample mean, we would call this distribution a sampling distribution, in particular for the sample mean. Now, I mentioned that the sample means, those sample statistics that we were finding, vary a little bit. So let's do a deeper dive on the topic of sampling variability. Suppose there's an election and the two primary candidates are candidate D and candidate R. Wonder what those could represent. Suppose in a particular survey of 1,000 U.S. citizens, so there's our sample size, 46% plan to vote for candidate D and 47% plan to vote for candidate R. But in another similar survey, 48% plan to vote for D and 46% plan to vote for R. Now, this is certainly something that could happen. This doesn't mean that one of the samples is messed up. These are pretty similar, reasonable numbers, but there is a bit of difference. This is an illustration of sampling variability, which is the reality that random sampling is going to yield different results because it's going to be dealing with different samples. And though these differences will be less pronounced with good sampling, even if the samples are good, there is going to be a little bit of variability. In theory, the true, that is population, proportion of voters, say for candidate R, does exist, but the population parameters are usually unknowable, all right? So the population proportion of voters for candidate R, it does exist. There is an actual proportion of the population that voted for candidate R, but honestly, it's unknowable, all right? Unless we have some very, very accurate data that we commoners don't have access to. And what we often have to do in statistics is take a guess at that true population parameter. And really the rest of the year is about how we deal with that conundrum, that the true proportion, or in another context, the true mean or the true pick your parameter, are essentially unknowable. How do we deal with that? How do we use sampling and other techniques that we've learned about this year to deal with that problem? That's what really the rest of the year is about. The distance between a sample proportion of voters for candidate R and the true proportion of voters for candidate R, assuming we somehow knew it, is called the sampling error. In other words, if the true proportion of voters for candidate R is in fact 46.5%, the sampling error for both of the samples that I discussed is 0.5%. That first survey featured 47% voting for candidate R, and the second featured 46%. So they're both 0.5% off the true proportion of 46.5%. About now is where things start to get a bit confusing sometimes. So buckle your seatbelts, put your thinking caps on. We are going to discuss the sampling distribution of sample proportions. Honestly, what I found is a lot of what makes this confusing is the overuse of the word sample and sampling. Try your best to follow what I'm describing here. Suppose we were to perform a simulation, all right? We talked about simulations earlier this year, in which we interviewed 1 million samples, okay? So we have 1 million samples. How big are those samples? Well, they are of size 1,000. And each time we took a sample of 1,000, we recorded the population that plans to vote for candidate D. Okay, this is purely theoretical, of course. To perform this simulation, we assume P, that is the proportion of people planning to vote for candidate D, is 47%. That's a reasonable assumption. We could use a calculator feature like randint and have the calculator select random numbers, assigning 1 to 47 to be voters for candidate D and 48 to 100 to be voters for someone else. This is a simulation. This is not real life. We are not actually finding 1 million samples of size 1,000. That would be absurdly expensive and really, honestly, a waste of time. We're going to simulate this using technology. Once we select 1,000 random numbers, we can find p hat, that is the sample proportion for that sample. Now, this simulation is a lot of work too. Selecting 1,000 random numbers, that's a lot. But with computers that the writers of our book used, they were able to do this quickly and efficiently and produce the graph that you see. That is 1 million simulations of samples of size 1,000. The histogram above is the result of 1 million samples of size 1,000. On the x-axis, we have the proportion of voters for candidate D, and on the y-axis, we count the frequency of each sample proportion we obtain from a random sample. So sometimes our proportion was a bit on the higher side. Sometimes our proportion was a bit on the lower side. But generally, our proportion hovered around our predicted 47%. Does this distribution look familiar? The sampling distribution of sample proportions, that is the distribution you see right here of your p hats. Some of the sample proportions are low, some are high, but most of my 1 million sample proportions are somewhere in the middle. That is the sampling distribution that results from doing all those simulations, and it seems to fit that bell shape. And here's the big question. Is this a one-time thing, or is this true of sample proportions in general? If we find many sample proportions with the same assumption of what the true proportion is, do we always get that bell curve? And the answer is yes. As it turns out, Abraham Demoire, if you speak French, I am very sorry, my French pronunciation is terrible, proved that the sampling distribution of sample proportions will be, you guessed it, unimodal, symmetric, and, to boot, centered at the assumed population proportion, 47% in R case. Our graph fits DeMoire's criteria since the distribution is in fact bell-shaped and it is centered at our assumed population proportion, 47%. Now, if you had your thinking cap on nice and tight, you may have noticed something about the scenario I've laid out. Generating a random number that indicates a vote for candidate D or a vote for someone else constitutes a Bernoulli trial from Chapter 16. There is a clear success-fail. You either do or don't vote for the candidate. The trials we assume are independent, which in an election, that's not a really reasonable assumption to make unless you're really good at randomization. And the probability of success does not change. So assuming that is the case, these are Bernoulli trials. That means that we can use some of the properties of Chapter 16 to describe the distribution of sample proportions. And our sampling distribution of sample proportions is going to fit a normal model, not just any unimodal and symmetric curve, but the normal model itself. We know the mean of our sampling distribution of sample proportions, that graph on the prior slide, is 47%. Like all normal distribution curves, all normal models, the mean is right smack dab in the middle, and that's where we find our 47%. But we still need to find the standard deviation for our normal model. How do we do that? Well, we're going to let x, another random variable, be the number of voters for candidate D. Since x would fit a binomial model, it's a set of Bernoulli trials after all, given a number of trials, namely 1,000, and p, the probability of success, that 47%, the standard deviation for this binomially distributed variable is the square root of npq. We learned that back in Chapter 16. Also, p hat, our sample proportion, is x, the number of people who voted for candidate D, divided by the total number of voters. That's what a sample proportion is. It's a part-to-whole analysis. From that, it follows that the standard deviation for our sampling distribution of sample proportions is going to be this. Now, how did we get that? Well, we need to remember something. The standard deviation of a constant times a random variable is that constant, assuming it's positive, or we make it positive, times the standard deviation of the random variable. If p hat is equal to x over n, then the standard deviation of p hat, our sample proportion, is going to be this constant 1 over n times the standard deviation of x, which is square root of npq, okay? So from this step to this step is just a little bit of algebraic reorganization, and I'll let you think about why that's true. Here is the bell curve in question. It's a normal model centered at my assumed population proportion p with a standard deviation of the square root of the quotient of the product of p times q all over n. So we can regard the sample proportion as a random variable in its own right. And as a random variable, it has its own probability model, provided it meets a few conditions, which we'll see on the next slide. And that is also a theme for the rest of the year. You really can't assume that anything works automatically. Really, every process we're going to do requires you check a couple boxes before you do it. We call the probability model the sampling distribution model. That is an extremely important phrase. The model of a sampling distribution is a massively important term to be aware of. How do we model the sampling over and over and over again that I've discussed. And this is a sampling distribution model for a sample proportion. And these are the details, some of which I have already discussed. So this is straight out of your textbook. Provided that the sampled values are independent and that the sample size is large enough, and we'll talk about what large enough means, the sampling distribution of the sample proportion, or p-hat, can be reasonably modeled by the normal model, with mean being the assumed population proportion, and the standard deviation being the square root of that quotient that we have already discussed. So, how do we know that we are able to use a normal model to describe a sampling distribution of sample proportions? Well, you need to assume independence, that the individuals in the sample must be independent of each other. Now, how do we know for certain that the subjects are going to be independent? We can check two conditions, and the conditions are what I want you to really focus on. The randomization condition. Randomization is your friend in statistics, and that never goes away. For experiments, subjects should be randomly assigned to treatments, and for surveys, the sample should be a simple random sample, or if you have a really good reason, one of the other types of sampling, the stratified sampling, the cluster sampling, systematic sampling, just not convenient sampling or any of those bad forms of sampling. Just to clarify, a simple random sample is a sample in which all possible subjects are equally likely to be chosen and all groups of subjects are equally likely to be chosen. I will add to my own notes. We also need the 10% condition, which we introduced in a previous chapter. I think it was chapter 16. We're only sampling less than 10% of the population. Otherwise, we cannot assume independence. We also, as you may recall from just a moment ago, need a large enough sample size. The sample size n must be sufficiently large. How large, in fact? Well, we will check another familiar condition, the success-fail condition. We need to be able to expect at least 10 successes and 10 failures. This is a condition we saw in chapter 16. In other words, n times p, sample size times probability of success, is greater than or equal to 10, and n times q is also greater than or equal to 10. So we are finally how far into this video, and we are getting to an application. The CDC report that 22% of 18-year-old women in the U.S. have a BMI of 25 or more, a value considered by the National Heart, Lung, and Blood Institute to be associated with increased health risks. As part of a routine check at a large college, the phys ed department usually requires students to come in to be measured and weighed. This year, the department decided to try out a self-report system. It asked 200 randomly selected female students to report their heights and weights from which their BMIs could be calculated. Only 31 of these students had BMIs greater than 25. Here's the question. Is this proportion of high BMI students unusually small? Before we begin, we need to check a few conditions. We need to check the randomization condition, the 10% condition, and the success-fail condition. The department drew a random sample, so the problem says. So the respondents should be independent and randomly selected from the population. 200 respondents is less than 10% of all female students at a large college. That's a pretty safe assumption. And the success-fail condition. The department expected n times p, 200 times 22%, 44 successes, and consequently 156 failures, both at least 10. So we've met the success-fail condition, the 10% condition, and the randomization condition. Seems like we're good to go. Well, Let's look at the numbers here. The phys ed department observed a sample proportion of 31 out of the 200 students, or 15.5%, with BMI greater than 25. The department expected a proportion of 22%. That's what the problem says. With a standard deviation, which here's our formula, the square root of PQ over N is equal to this quantity right here, P being 22%, Q being the complement of P, which would be 78%, divided by the sample size of 200, and that's going to be 0.029. So the expectation, or the mean, they're the same thing, of our sampling distribution would be the assumed population proportion, which, as I've said, we're given, and the standard deviation we need to use a formula to get, but it's not so bad once we know it. From here, we would use normal CDF because the random variable sample proportion follows a normal model. So now we're going to go to the calculator. So here we are in the calculator. I've entered the information from the prior slide, and here we go. And that is a very, very, very low likelihood, assuming the CDC's proportion of 22% is correct, that we got data like we did, assuming there was no funny business. This self-reporting might not be as reliable as perhaps the university thought. Let's do another example. Suppose that about 13% of the population is left-handed. Cue the footnote. Whenever you see a statistic about being left-handed, there's always going to be a footnote because left-handedness is notoriously difficult to get a true proportion on, and I'll let you think about why that might be true. A 200-seat school auditorium has been built with 15 lefty seats. Some of you might not have known that these exist. Seats that have the built-in desk on the left rather than the right arm of the chair. And for left-handed readers among you, our textbook writers observe, have you ever tried to take notes in a chair with the desk on the left side? It's a little tricky. In a class of 90 students, what is the probability that there will not be enough seats for the left-handed students? This is a question that we can answer using our technique. So, first we need to check the conditions. We can assume independence. It is reasonable to assume that the enrollment of one left-handed student does not affect the likelihood that other lefties will enroll in the class. We can confirm that with randomization. The 90 students in the class can be thought of as a random sample of all students. Fine, not the kind of randomization we would hope, but that's what we got. 10% condition, 90 is certainly less than 10% of the population of all students. Even if the school is small, we could think of all possible students that could have gone to the school. Success fail, we are expecting 11.7 successes and 78.3 failures, both of which are bigger than 10. So, the population proportion is 13%. That's what we're assuming the true proportion of lefties is going to be. The conditions are satisfied. We can model the sampling distribution of the sample proportion with a normal model, mean of 13%, and standard deviation of, here's the one we need the formula for, the standard deviation for the sample proportion is going to be the square root of PQ over N, which is 13% times 87%, that's Q, the complement of 13%, all over 90, my sample size of which is 0.035. So my model for p hat is normal, centered at our assumed population proportion, and spread according to this standard deviation. Now we're ready to find the odds that we don't have enough lefty seats for our left-handed students. We're going to use normal CDF, and we have our mean of 13%, our standard deviation, which we found, but what's going on over here? Now, remember, there are 15 lefty seats and there are 90 students. In the case that we don't have enough lefty seats, this would be our lower limit, 15 out of 90, and there would be no upper limit. We'd be going far up the right tail of the bell curve. This lower and upper limit, or lack thereof for the upper limit, gives us the likelihood that we don't have enough lefty seats. So one more time, we're back at the calculator. I've entered my lower, upper, mean, and standard deviation. Let's do it. And those are pretty reasonable odds. Certainly an event that could happen, coming in at about 14.7% odds that we do not have enough lefty seats. Man, lefties have it tough. Lefties out there, I salute you.